Hello and welcome to Simulation TV. My name's Shawn Gedman. I'm a product support specialist with Autodesk, and today we wanted to go over a topic on choosing a suitable mesh type for your model in Simulation Moldflow. So our problem description and main point of for this presentation is going to be how to choose your suitable mesh type for your part. We have a few mesh types that we'll discuss and go into further detail in the next couple of slides. So some key learning objectives that we have during this presentation will be, one, we want to cover some key learning, cover some mesh basics, get our terminology straight so we have a good understanding for the rest of the presentation. The next thing we'll also look at is review the mesh types available in Insight and some of them in Advisor as well. The assumptions made by each mesh type during the analysis, and finally choosing a suitable mesh type for your model, particularly based on geometry. All right, so to start off, you might ask, what is a mesh? A mesh is basically a division of a physical domain into smaller subdomains, and these subdomains we would call elements. And based on these elements, you'll notice that there are nodes, and these nodes will be at the vertices for the triangle and tetrahedral elements that we'll discuss in further detail, and they're also on either end of beam elements. And these points focus on, or these nodes are used to calculate certain results. They're going to be recorded at these nodes. They also determine a coordinate position in space for the model and serve as places to place injection locations, coolant inlets, and constraints. So just to cover the four mesh types that we do offer, the first one is a beam element, and we commonly refer to that as a 1D element, midplane, dual domain, which is also referred to some as 2.5D, and of course tetrahedral, or the 3D solid element. So we'll start off talking more about beam elements. So typically beam elements are used to represent melt delivery systems, cooling channels, things of that nature, whether it's a hot runner, cold runner, sprue, gate. That's what we typically use these for. We assume an axisymmetric circular tube flow assumption here, and that's the nature of the beam element that we use. The next thing is that we should be aware of is that these beam elements, they can be modeled in many different shapes, half rounds, tetrahedrals. When they are non-circular shapes, we're actually going to convert these into a circular tube. The solver will behind the scenes to carry out the calculations. And also heat loss is considered around the entire perimeter of the shape, as it should. Some of the other things we look at, we have to account, or we want to use a Bagley correction to simulate, let's say, juncture loss, which is basically the hydraulic loss from large contractions, converging flow maybe through a gate. It helps with accurate pressure predictions. So when you look in the material properties, you may see a C1 and a C2 constant. That's what these values are for, and they help with the calculations here. And the one thing or limitation that we should be aware of is that beam elements cannot account for shear-induced imbalances. That's something that we can do, but you would want to model your feed system in, say, tetrahedral elements or a 3D mesh if this is something you're particularly interested in. On to the next two mesh types. I kind of summarized or lumped the midplane and dual domain mesh types together because they have a a lot of the same application, and their suitability is for thin-walled parts. You know, what is a thin-walled part? Most of the time you can look at a part and determine if it's a thick and chunky part or if it's a thin-walled application. But if you need a kind of a guideline to go about, I would say you would want your flow length to be at least 4 times the thickness of your part, and we would say that's a thin-walled part and would be suitable for dual domain and mid-plane mesh type. Now, these two mesh types, when you're going through the flow solver, they are using the generalized Healy-Shaw model. This is a model that isn't unique to Moldflow particularly, or so you can go do a search and determine more, get more details on this. But the key points we want to be aware of is that it's calculating laminar flow of a generalized Newtonian fluid. Inertia and gravity effects are ignored, which is okay because thin-walled parts, this is not typically an issue, so negligible impact. Same with heat loss, it's ignored on the edge elements. Typically with thin-walled parts, this makes up such a small surface area of the part that it's negligible as well. So those are the assumptions that we need to be aware of with these mesh types. And when the solver is working, basically what happens with the mid-plane dual domain mesh is that you have an injection location at a node, and this is the starting point for the flow calculations. And the flow will grow from that point, expanding outwards to the connecting nodes and growing and growing. So a node is filled, properties are calculated, it progresses on to the next node in line. And the assumption with this is that the melt temperature is homogeneous when entering the mold when you're using injection location only here. Dual domain is a unique mesh type to the Simulation Moldflow products. So I put together a slide that is covering some of the things that occur with this mesh type that do set it apart from some of the others. And what it is it's just a plate element, triangular element that we would see in the mid-plane mesh type, but it gives us a chance to see a 3D representation. So there are certain features on your part that might not be good for a mid-plane model, or features you can't represent with it. However, 3D might not necessarily be a good fit for it either. So this is where dual domain comes into play. And it basically uses what we call connector elements to connect the top and bottom, or the core and cavity half of the part. And what this is you don't see it, it's done automatically with the mesher. And these elements have zero flow heat resistance. And basically what they're doing is keeping the flow synchronized between the core and cavity halves, and making sure we have a accurate flow prediction here. Some things that we need to be aware of is that thicknesses are determined by matching the top and bottom, or core and cavity elements. So we need to make sure when we look at our mesh statistics that we have at least 80% or higher match ratio. If we don't, then we need to be aware that there might be some thickness interpretation issues, or we could suffer inaccuracy. So if you're on that fine line, maybe generate a thickness plot or look at your thickness diagnostic to see if this is going to be a problem for you. And the final mesh type is our 3D mesh. This is a true solid mesh, so we have elements through the thickness, nodes through the thickness. So what this is good for is thick and chunky parts, because we have some complex flow patterns that generally go on within these components. Let's say electrical connectors, things of that nature that we need to simulate some thicker geometries. And this uses a Navier-Stokes model, and again, this is a general theory that you can search online and research more if you wish. And basically, solves for the pressure, temperature, and the velocity components at each node. And the benefit to this as well is that it considers heat conduction in all directions, so we're not neglecting heat transfer on edge elements, which is why this is a great mesh type for those thick components, thick parts where you know, the sides might make up a significant amount of surface area and could impact our results. It also offers inertia and or gravity effects, so you can see the effects of inertia and gravity. You know, 3D parts, they could be fairly voluminous, so when you inject into maybe a cavernous area, you could see some effects from gravity, especially if you're trying to simulate jetting, things of that nature. So in this case, it would be important to take this into consideration. The one thing that you definitely want to be aware of with a 3D mesh is that it will take more resources on your computer. So I wouldn't say 3D is always the best mesh type to run in every scenario. Each mesh type has its place and its benefits and disadvantages. So these are things we need to be aware of when setting up our model, and some of the things we wanted to cover during this presentation. Hopefully the theory, we're all clear on that, and there aren't too many questions, but at this point we're going to move on to a live demo of just how to import models, mesh models, and I'll show you some examples of the different mesh types. All right, so here we're going to do a live demo for a model just to show you a couple of the mesh types and you know, get you familiar with what they look like, maybe some of the things we need to look at for when generating them. So first thing we do, like anything, is you start from left to right or top to bottom, because it's meant, you know, to be an intuitive workflow. If anything's grayed out that you want to do, you just missed the previous step. So in this case, right in the corner, we're going to import a model. We have this plank. The first thing we're going to do is a 3D mesh, a solid 3D mesh. So I change this to a 3D mesh. If this is something, or if you mess up on this section, you always have the option to change that after this menu, so don't worry about that. All right. So we have our simple geometry. We have our mesh type set here. And again, like I said, if you pick the wrong mesh type, you can always change it by right-clicking on here and set mesh type, and you can just change your mesh type. Another option would be to go up here and you can change your mesh type here as well. So when doing a 3D mesh, we basically import our part and then we can right-click, generate mesh. I'm going to do a global edge length of probably about 4 millimeters, so we're not going to take up a lot of time here on meshing or getting a really, really fine mesh for this exercise. There's a preview button right here as well. If you wish to get a rough idea of what your mesh density is going to look like, that's a good place. For 3D, there are some CAD options here if you want to do a chord angle. This can help to better represent rounded features, holes, things of that nature. Another tab, the Tetra tab. And this is unique to 3D, and that's allowing you to specify the number of layers through the thickness. Usually 6 is adequate. If you're going to go into something where you want to simulate something unique, such as maybe a fairly detailed fiber analysis, and you want a good resolution, or you're going to simulate jetting or gas assist, you may want to set this at least 10, possibly higher, to get that resolution within the part. Max edge length through thickness is another setting. I typically leave this alone, and this is kind of a fallback for, or kind of a ceiling, we could say. And you have 6 layers through the thickness, but let's say you have some areas of that part that are significantly thicker, and 6 layers just won't do it. But you don't want to mesh your entire part 12 layers or something fairly high like that if not necessary. So that's what this does, is it's going to detect when an area might require a layer to be, let's say, thicker than 1.97 millimeters in this case, and if it exceeds that, it's going to put more layers in that model for you. So think of it as a ceiling. Surface mesh optimization, that's an option that we use for generally it will help optimize your mesh, and what it is it will give you finer mesh in areas that need it, or coarser mesh in areas that may not need the representation. Some other options that we have here, we have biasing, and what this is set by even distribution by default. You can do a bias ratio if you wish, and what that's going to do is either concentrate your layers towards the center of the part or more towards the outer surface of the part. So if you're looking at maybe some shear effects or fiber orientation where you really want to maybe view more of the outer layer of the part or towards the surface of the part, we can set some biasing up here to focus our resolution in those areas. So at this point, I'm going to mesh the part. This will be rather quickly since we used a coarse mesh. Now what we have here is, you see our 3D part, and we have our mesh, and that's it. That's all that's involved. If we take this part, we can actually cut this. Or I'll just delete them. And we zoom up there. You can see we have our nice solid mesh through the whole thickness of the part. We've got 1, 2, 3, 4, 5, 6 layers, just as we specified, and that's that. So next, to forego the import process, it's still the same. You just choose a different mesh option or mesh type. So I have this part, it's imported already, and what we'll do is take a look at the dual domain mesh type now. So again, just mesh, generate mesh. I'm going to set this at 4 millimeters again. We don't have as many options with the dual domain and mid-plane mesh because you just don't need it, such as layers through the thickness, things of that nature. So we have global edge length, submerged tolerance, mesh match. This is, as we mentioned, important for those thickness interpretations in the model. So we want to have a good mesh match, and that's what this will do. It will help us to optimize that. If you're going for maybe a more uniform mesh, I know a lot of people prefer a uniform looking mesh, you can always turn this option off, and it will give you a more uniform surface mesh, we could say a prettier mesh, but just check your mesh statistics to make sure that you're falling within the mesh match ratios, as I mentioned before, at least 80%, hopefully 85 or greater. And of course the CAD tab, we have the chord angle control again for better refinement on round features or holes. So at this point, I'm just going to mesh the part. It's pretty quick. And if we take this part, cut through the center, zoom in, you'll see it's a hollow part. We're still getting, when we run the analysis, we're still getting results through the thickness. we're still accounting for them. We're still seeing the shear effects through here, fiber orientation, all of those things. It's just that we use a unique method for layering method for this, so it doesn't require an actual mesh to be present there. Now the final mesh type is a midplane. So this one, you bring in your model just as you would your 3D model typically, and what it'll do is when you mesh this, it should midplane it for you. So again, we're set to midplane, and here we have a global edge length, a merge tolerance, and then the NURBS tab. And the NURBS tab, it's going to give us a few options. You can do chord height again here for the refinement on round features. You can optimize aspect ratios by curvature control or proximity control, things to that effect. And you can research all of these topics in more detail if you wish right here in our help topics. They're all outlined in there. So at this time, I'm just going to mesh this at the 4mm edge length. And you'll see we now have just a surface essentially. And if we turn our CAD surfaces back on, you can see it's right at the midplane of this, which we would expect. Just be careful with this particular mesh type because with the danger of any mid-planing tool, sometimes there can be difficulties in very large or complicated models. It might not pick the mid-plane as you might want it to on there, and this mesh type is probably the more traditional, the one that's been around since the beginning of time. So running in midplane, you typically have a lot of results available when compared to the other two mesh types. They still have plenty of results, but midplane has a pretty strong following. It's been around a long time. Now, some things I mentioned about mesh statistics, and you know, of course you want a clean mesh. So what you want to do there is you can come into here and you can either run through mesh statistics, take a look at it. There's a mesh repair wizard. It'll take you through step by step just to make sure that your mesh is adequate. Most of the tolerances they have set here, you can go through, see zero overlaps, aspect ratios. It's going to check for collapsed issues, and you can see tolerances. They'll be set for like a target aspect ratio is 10, really 7:1, 10:1 is optimum for dual domain midplane. You can see we have that here, and it's going to tell you what you're violating if any areas have problems with that. So this is the automated tool. It's a good tool to use before going into maybe some manual repair. It will also give you an opportunity to identify these through a diagnostic tool. The other options, the mesh statistics. This is just going to give you a readout or the statistics on your mesh. And you know, of course, with this, you need to know what to look for, and what to look for can be found in the help. And if you have further questions on that, I'd guide you to this help topic, which is mesh diagnostics. It's going to tell you every diagnostic that we have for each mesh type. The yellow is midplane, the blue is dual domain, and the red is 3D. And as you probably saw, we have those same indicators here to signify what mesh type your model's in or currently meshed in. So good help topic to go to if you're struggling. Then it'll tell you what's available, what to fix. There are also some tutorials in here as well that can guide you through some mesh exercises if you wish. And that would conclude our presentation for today. Thank you for joining us, and have a great day.